So, you want to find a black hole. Let's get started by evaluating some of the tools available to us. Obviously, when astrophysicists study objects in the sky, they typically use telescopes. Telescopes allow us to collect light and produce images of the features near a black hole. But there are many different types of telescopes, so it's important to choose the best one in order to be certain that what you are in fact looking at is a black hole. You may have seen a telescope like this one that we have at the University of Alberta's observatory. This is a fairly standard type of telescope that gathers and focuses light using curved mirrors, called a reflecting telescope. Historically, it was much easier to make lenses rather than mirrors, so early telescopes like the ones used by Galileo, used to discover the moons of Jupiter, are called refracting telescopes. In modern times, it is much easier to build large mirrors than it is to build large lenses. So the enormous telescopes used in astrophysical research are reflecting telescopes. When we talk about ground-based reflecting telescopes, the majority collect light in the optical spectrum. That is, the light which humans can see with their eyes. For example, this Schmidt-Cassegrain telescope has two mirrors, a big primary mirror at the back and a secondary mirror at the front. It also has a corrective lens, but this is quite an expensive telescope. The purpose of a telescope's primary mirror is to collect as much light as possible from faint objects. The larger the diameter of the mirror, the more light is collected. Think of it like a big bucket. And it becomes easier to see faint celestial bodies. But a larger mirror also means a larger, more expensive telescope, which is a trade-off that we have to pay in order to get better resolution of distant objects. For example, if something looks like a blurry smudge through a small telescope, a bigger telescope will produce a clearer image without changing the magnification. Larger telescopes may also allow for more magnification, but magnification should be second to the mirror diameter. Dim and distant astrophysical objects like nebula and galaxies are easily resolved by small telescopes with low magnification, but they require lots of light in order to be visible. My family invested in a 4-inch Newtonian reflector when I was young. It was a present from my dad. This telescope encouraged my interest in astronomy, and it taught me an important lesson. If you're purchasing a telescope, do not purchase one that advertises its magnification. This is a sign of a poor quality telescope. Instead, a good quality telescope is described by the diameter of the primary mirror, or for a refracting telescope, the diameter of the primary lens. For instance, our telescope at the University of Alberta has a huge 14-inch diameter mirror. Sorry about the imperial units. They're still common among telescope manufacturers. The 14-inch mirror can collect much more light than smaller telescopes, revealing dim structures in the night sky like the Ring Nebula in the constellation of Lyra. Large, ground-based research telescopes, like the two Gemini telescopes in Chile and Hawaii, have mirrors that are 8 meters in diameter. But that's a drop in the bucket compared to some ongoing construction projects like the Extremely Large Telescope, or ELT, which will have the largest compound mirror of any telescope in history. The ELT's compound mirror will have an effective diameter of 39 meters, itself made up of a collection of smaller mirrors that can be aimed independently. Scientists call this independent motion adaptive optics, because the mirrors need to move in order to cancel out the turbulence of Earth's atmosphere. Often, they measure these disturbances using powerful lasers. Here's the Subaru telescope calibrating its optics. The Earth's atmosphere is turbulent, and the rapid motion of air pockets in the atmosphere smears out the light from stars, which makes them appear blurry. What would be the best place to construct these massive telescopes? Of course, you'd want to build them near the top of a mountain. This is not to get them closer to the stars. By situating the telescope on the top of a mountain, we decrease the amount of atmosphere between the telescope and the stars, which improves the seeing. Seeing is actually a technical term used by astronomers. If the atmosphere is calm and the images seen through the telescope are crisp and steady, we say, the seeing is good tonight. There's an obvious way to avoid the blurring effects of Earth's atmosphere. Launch a telescope into space. Of course, you're probably already familiar with the Hubble Space Telescope, but did you know about its successor, the James Webb Space Telescope? The telescopes that we've just looked at are all visible light telescopes, also called optical telescopes. These are telescopes that can detect light visible to our eyes, along with some neighboring wavelengths in the infrared and ultraviolet light. This type of telescope is capable of viewing stellar companions of black hole binary systems. However, since most of the energy emitted by a black hole is in parts of the electromagnetic spectrum that our eyes can't see, we need to investigate other types of telescopes capable of detecting light that is invisible to our biological eyes. Black hole jets emit radio waves, part of the spectrum emitted by hot plasma within the jet. So a radio telescope is an important tool for black hole astronomers. Remember that radio waves are the lowest energy and thus the longest wavelength part of the electromagnetic spectrum. Since radio waves are electromagnetic waves, or photons, they still travel from the black hole towards us at the speed of light. Radio waves have long wavelengths that range from millimeters to meters in length, which is the reason why radio antennae have to be very long. You might be familiar with radio waves that you receive when listening to a radio station. For example, if you were listening to a station at 102.9 on the dial, meaning that you were capturing photons with frequencies of 102.9 megahertz, they would have a wavelength of approximately 2.92 meters. Recall a green laser have tiny wavelengths, measured around 532 nanometers. Radio telescopes like the ones that make up the Very Large Array, which was featured in the movie Contact, are usually large dishes instead of antennae. Light waves from neighboring radio telescopes in an array can be combined using a technique called interferometry, which allows the whole group of telescopes to act as one large one. The effective size of a radio array is similar in size to the distance between the dishes. The largest single-dish telescope, called FAST, the 500-meter aperture spherical telescope, is 500 meters in diameter and located in China. If you've seen the James Bond movie GoldenEye, you might recognize the Arecibo radio telescope in Puerto Rico, where Bond defeats Trevelyan. Radio telescopes located at different parts of the Earth, as shown on this map, are being used as one Earth-sized radio telescope called the Event Horizon Telescope. It's observing Sagittarius A star, the supermassive black hole at the center of our galaxy. We'll discuss the Event Horizon Telescope's observations in Module 10. On the other end of the electromagnetic spectrum, at high energies, black hole accretion disks produce X-rays. So an X-ray telescope would be the best tool in our hunt for black holes. But there's one problem. Earth's atmosphere absorbs X-rays. Actually, that's a really good feature for our atmosphere. If X-rays could make it through the atmosphere to the ground, we would constantly be irradiated. X-rays have even more energy than ultraviolet light, the light that causes sunburns. So tanning under the X-ray light from a black hole would burn you to a crisp. Don't worry though, X-rays used in doctors' offices and dentists' offices are produced in safe quantities. Radiation therapy used to treat cancers are a good example of the damage X-rays can do, to the cancers of course. Since the Earth's atmosphere protects us from cosmic X-rays, an X-ray telescope needs to be launched above the atmosphere and into space. This diagram shows how much of the Earth's atmosphere blocks light with different wavelengths. Visible light and radio waves can penetrate through the Earth's atmosphere. However, gamma rays, X-rays, ultraviolet and infrared radiation are blocked by the atmosphere, so telescopes that can observe light at these wavelengths usually orbit the Earth. The Chandra X-ray telescope is an important black hole detecting telescope. It allows astronomers to view X-ray images and spectra of black holes. Chandra is named after the Indian physicist Chandrasekhar, who is famous for his theoretical work on black holes, neutron stars, and white dwarf stars. He also preferred to be called Chandra. Another orbiting X-ray telescope is called the XMM Newton. Although Chandra is a better telescope for creating detailed X-ray images, XMM Newton is a better telescope for determining the wavelength of those X-rays. A new telescope called Athena, with a planned launch date in the year 2028, will combine the best features of these two telescopes. NuSTAR is another X-ray telescope that orbits the Earth, but the long length of this telescope allows astronomers to view much higher energy X-ray photons than the Chandra Observatory. This allows NuSTAR to detect processes taking place very close to the black hole's event horizon. A nice X-ray telescope called NICER was recently mounted on the International Space Station and is orbiting the Earth on the ISS. NICER is designed to accurately give the time of every X-ray photon that strikes it. This allows NICER to detect rapid changes in X-rays that are emitted by black holes and neutron stars. Astronomy that makes use of the accurate photon timing is sometimes called time domain astronomy. This is just a small selection of some of the telescopes that are used to study black holes. A completely different way to detect a black hole is through gravitational radiation. Of course, we'll learn more about gravitational radiation in Module 10.